There's two options. We do KVL, KCL, or find some kind of Z equivalent to find the output. Two options. I'm giving them quite some time. We can look at different currents. And trying to come up with the transfer function of capacitor voltage with respect to input current. Creating a transfer function and then doing some frequency analysis on the RLC circuit. All right. Here's my transfer function. I guess I did the impedance method, but both of them are obviously available to use with full body. We know that it should be second order. So for our full body stuff, this is second order. I've got my diagram. Obviously, input is the current, and the output we're looking for is capacitor voltage. So let me just talk through this a little bit. Again, you can choose either option, but one way I can look at it is I can really solve this transfer function like I'm solving for the output voltage. If I just draw two terminals out of here, that voltage is going to be equal to the capacitor voltage. So first, I can take R and L and combine them into one equivalent impedance because they're in series. So that's just going to be R plus LS, or LS plus R. That's on the top left. That's the equivalent one. Then what I can do is I can combine these two that are in parallel, and therefore now I have this one current going through here that's still equal to the same output voltage. So we can take those two, add them in parallel. That's this part right here. If I'm adding them in parallel, that's adding up the reciprocals. And so we get Z equivalent to be this. And once I have that, this is my Z equivalent to. This is the relationship between E out, which is the same as capacitor voltage, with respect to I in. because E out is equal to Z equivalent 2 times I in. So that would be our transfer function, which is second order. It is stable. And from there, then we could plug in the numbers. Nothing special about that. So we've got our values here we're going to plug in. And we get our transfer function that looks like this. So this is our second order transfer function. Once we have that, then we can do all the frequency analysis on it. We can do the Bode plot. But this test, there will be some parts where you've got to at least get to the transfer function. That's doing Bow-Body. It's all going to be hydraulic problems. But maybe you prefer that over circuits. I don't know. Oh, okay. All right. So it'll be electric or mechanical, some kind of transfer function. So the next step is, but once we have that, next step is to try to find frequency response to the beginning of the top right. So now that I know how the system is constructed, how will it respond? What is its output going to be like when I give it this sinusoidal input? All right, so for the next step, you are putting it in standard form. Hopefully, yeah? Standard form, transfer function. Then, if I want to find the frequency response, that's for a given frequency, that's where we're going to use that sinusoidal transfer function. That become omega I. And if I have an I squared, that becomes a, if I have an IQ, I don't think I have that actually, but if I had one, but if I had IQ, what are we talking about? Oh, okay. IQ becomes negative 5. And then from there, you're trying to get it simplified to one real part, one imaginary part for the numerator and denominator. From there, plug in frequency bit, probably 100 radians per second. So we can solve for magnitude and phase. Those are the two things we need to find to be able to find the steady state frequency response for circuit. Well, this is embarrassing. I didn't put it in standard form. Wait, did you get a similar magnitude and phase though? But you got different magnitude? Now it shouldn't affect that. Let's see. So standard form would be standard form would be 5 omega I plus 250. This is the sinusoidal transfer function. We have it would be 50 omega I plus 2500 minus omega squared. Does that look better? So standard form again, this s squared, right, is become omega I, all of that squared, so I squared becomes negative. Looks like that. So as we change the frequency, magnitude is going to change. Is going to change. So we can say at a frequency of 100 radians per second, by the way, this is radians per second. If they gave you something in hertz, how do you change hertz to radians per second? Yes, you multiply by 2 pi, because there's 2 pi radians per every cycle, and hertz is cycles per second. In this case, didn't have to worry about that. We have a frequency of 100 radians per second. So in standard form, what this becomes is this is going to be 500 I plus 250. And then we have 5,000 I plus 2,500 minus 100 squared. So it's negative 7,500. Now, either way, this should still give us the same answer. Everything is just grouped up a bit. $500 squared. Yeah, we still should get the same magnitude and same phase, even if it's in standard form or not. Now, standard form is going to be really helpful when we're doing the Bode plot. I need to have it in standard form to be able to find natural frequency, all that. So it's a good practice to do it right away. Not like me. We have standard form, we've got standard form, we've got an imaginary term, we've got a real term. Now we take the magnitude up top over the bottom. We should get this magnitude. This is my amplitude ratio at a frequency of 100. Again, that can change. Lower frequency, I expect it to be a higher amplitude ratio. But we're probably past the corner frequency. So we see a really small output, 6% of the input. When it comes to phase, we do numerator minus denominator. If, now this is in um, uh, the fourth quadrant right here. That's what's going on here. Or wait, no, this is second, because this is imaginary over real. In the second quadrant, what happens is if I do this and I get a positive number, I cannot have a positive phase angle. It always has to be trailing. I can't get ahead of it. It may look like it's slightly ahead, but we have to subtract pi. So we get a negative 1.45. So if you end up with a positive number, subtract pi, and we get our negative phase angle. Once I have magnitude and phase, we can plug that in to find our capacitor voltage at steady state. So we can find together these combine to make the output amplitude, which is 0.31 volts. That's what this should be, volts. And then that should be that. So we can find our output voltage from the transfer function. Okay. Now, you already have it in standard form. So if it comes to the Bode plot, now we can actually look outside of just 100 radians per second. How does the system respond to different frequencies? Is there a resonant frequency? Where's the corner frequency? What is K? What's our starting point? We can find all of those things. So let's just finish this one out. I think I have one last example, but I think I'll let you try it on your own as practice. So we'll finish this one out and end early. But let's try to, again, get some Bode plot practice. How could we plot this? What pieces of information do we need now that we have it in standard form? But if you have questions about this, I'll walk around and we can talk about it. A little more time. We just want to find from the standard form what is K, what is natural frequency, what is damping ratio, and then will we have a bump? Okay, where does that bump occur? What is the resonant frequency? And then how it would sort of look. That's some stuff. Okay. Here is when I take that standard form. Well, the first thing we can find natural frequency. Now, some of you are like, what do I do with that 5s on top? Well, for our, at least what we can do with it, we're just going to forget about the 5s on top. Now, our MATLAB plot, if I plotted this in MATLAB, it might be slightly different. However, the DC gain is still the same. It's going to be, I could just say all the s's go to 0. I'm left with that. K is equal to 0.1. That's the same. So if I take 20 log of 0.1, that's equal to negative 20 decibels. That's my starting point on the Bode plot when it comes to magnitude. We can find the natural frequency. Then from that, we can find the damping ratio. And since damping is less than 0.7, or root 2 over 2, we know that there will be a bump, but because damping is pretty high, we're close to 0.7, that bump is going to be quite small. And so I'm just going to show a little bit of a bump. That means that my resonant frequency also is pretty different from the natural frequency. Once I plug it into this equation at the bottom, we solve for resonant frequency. That's 35.4. That's about 15 radians per second slower, so lower than the natural frequency. That's where the peak of the bump occurs. And again, that's what damping does. If I have no damping, it's a really high bump. And then as damping increases, the bump goes down and it shifts to the left to lower frequencies. So this is basically how our graph would look. It drops by 40 decibels per decade. For the phase angle, again, that point where it hits the halfway point is going to line up with the natural frequency, 50 radians per second. And then you don't necessarily need to know this, but the phase angle, if I have a lot of damping, this is also a lot smoother, the transition from 0 to negative 180. If I have really low damping, this phase angle is a pretty quick transition. So damping affects both graphs in that way. Oops. All right, so that comes out of the standard form transfer function. Yeah. How high to make the bump? Great. So the other question I had was how, let's say you wanted to find the transmissibility or the magnitude at the resonant frequency, which is where the bump occurs. Wow, you had the perfect question. How high should that bump be? Can you determine that number in decibels? What do you think? Probably, yeah. How? Is there a way, if we have a frequency and we have a transfer function, to find the amplitude ratio or the magnitude? All right, let's change the question. The slide before this, what did we do? We found the frequency response, we found the phase and the magnitude at a given input, right? So we were using a frequency of 100, plug that in, and we solved for magnitude and phase. Guess what? You can do the same thing. Once you know the resonant frequency, you can plug that. And so instead of using 100, I would use the resonant frequency of 35.4. I would plug that into the sinusoidal transfer. And so with that, then we could actually solve for the magnitude. We take 20 log of that, and that'll give us our decibel. So that's how you can find the actual value for that bump. Should we do that real fast? You don't want to? Okay. That's how you do it. 20 log, once you plug that in, it would be, I don't know, in this case, maybe negative 18 or something like that. I don't know if I've actually done it. But hey, you can practice it. So that's how you can actually know it. Now, if you don't, yeah, you have to know the transfer function. In this case, to plot it. So you already have the transfer function. You can do it that way. All right, let's see. That was our circuit problem. This is a low pass filter. It allows low frequencies. 50 is kind of the cutoff here, and then after that, it drops off pretty fast. So this is a low pass filter. Now, we've already done this example before. You can definitely, in the next 2 days, you can work on it. You can pull from homeworks 1 and 2, just like, can I create a transfer function? Can I find the frequency response at a random frequency? You can do that. So it's kind of up to you how you want to practice. I have students take homework problems, put it in the chat, and say, hey, make a problem similar to this. So that's another way you can practice too. But anyways, we've done this one before. It's always good to review mechanical systems. There will be some mechanical as well on the test. So how could I create the transfer function? It's all about the transfer function. Once I get there, I can look at Bode plots. I can look at frequency response. That's really what this topic is about. So I'm going to post these. Yeah, so you can practice it. So I'll post these slides right after class. And is there anything? Other questions maybe that you had on the homework that didn't quite make sense? You just turned in. I hope to grade them today, maybe later today, just so you get some feedback before taking the test. All right. Okay.